Hello, everyone. Here I can see you, I can hear you. And for the online, can you guys hear us? Or...
Yes.
Okay, that's great. Okay, so I just want to first ask you about your homework. So did you try to take a look on the assignment? Okay, so I given more time for submitting. So it will be until this Sunday. So before meeting next time, it will be always like this. There will be enough time for submitting. Even that, I'm sure after having the correction, you may like just submit the correction. But I will be appreciating each time after each class when I will be checking the list of submissions and I will see those who are submitting correctly like before the due date. Okay, so we will start with the BFS, but before that, we go through like what we did last time. So in the AI class, we first start with the definition of AI, general one, like a more deep like definition, and then we went through solving search problems. And in order to do so, we were introducing like some terminology, like we were a little bit familiar thanks to the quizzes and discussion we had with terms such as agent, states, state space, goal state, path coast, and so on. These were very useful to introduce some algorithms, search algorithms. Some were informed algorithms, where we know exactly if we are, let me say, moving towards the right direction or not, direction towards the goal for sure. And some other algorithms, they are not informed, uninformed search. For the informed search, there was, and we are going also to review this after like going through the correction of this exercise. So there is kind of heuristic function, which is going to guide the algorithm. There is some function H or F or G. We will see it depends upon like on the algorithm. And this function is going to tell you if you are near or not. Using these functions or not will differ and produce different names of the algorithms. For example, the A star, or we will see that in details later. And if we are not going to be based on this like information, we are going to be in the context of an informed search. And in this case, we were starting with the BFS algorithm, and we went also through the DFS one. Both like may have variants, and each search algorithm we are seeing now, you can find different variants, means different people, could be like researchers, normal people, who are coming with ideas to enhance or to ameliorate that algorithm. To ameliorate in sense like when we were checking the performance, sometimes we work on the optimization in terms of time, in terms of like cost, space means on the disk or memory, I mean, and it depends, okay? So we are going to see like some important algorithms and few variants from each algorithm. So this is what we already started with last time. And now we have this like problem with the BFS. So we are trying to solve. First, we are going to use the very simple version, the breadth first search algorithm, to explore this graph. Okay, so the idea last time was that we are going to focus on solving such problem while exploring the search tree. Okay, so this is what I was asking. We want to explore this graph and we will represent our solution as a tree. Okay, so for the BFS, we may see like two different like solution, starting from the very basic one, which is like entities. Everyone is now going to try to solve this exercise. Is supposed to think like this. So I am going to explore this graph, and we already said last time that we have S here is the initial state. Sorry. Okay? From S, I can go to other states like A, I can go to B, or I can go to D. For each time I have the cost mentioned on the arrow. For example, for going from S to E, it will cost me 5 units. From going from S to B, it will cost 9, and from S to D, it will cost 6. Sometimes I can go, for example, from S to B, but I cannot go in the opposite direction from B to S. Sometimes I can go in both directions, like from S to D or from D to S here. So how to explore this given the BFS? So we start with the very first, the very basic solution of the BFS here. So first we will explore which state. You ask yourself, from among all these nodes, where can I be at in the start? In the initial states already mentioned, which is S. So to start exploring my graph, I will start with the initial state S. Now, from S, where can I go? I can go whether A or B or D. Okay? So in this same order, I am going to mention these nodes, which are A, B, D. A, B, and D. Okay? So if I am exploring all the nodes that I may go to from one state, so that state is supposed to be explored. Okay? So this is done. I am going to all the childs of this node. Okay. Now, if I am now in the case of BFS, so which data structure we use? Q. Yeah. So, which is? First in, first order. Yeah. So keep this in mind. So the first in is A. So I will start with A. Okay. And now from A, where can I go? To B and G. I can go to B or I can go to G. So I will go to B or I can go to G. Okay. Keep in mind that now I am exploring the child of A. So this one is done, but I am not in I see the goal like a jump. I'm there. As I am in the BFS algorithm, so I need always to respect the order, okay? So I have the A. After A, I will be visiting B and then D. Once I'm done with this first level, level 1, only then I can move to explore the next level, okay? So now we are done with the first, we are not done. Still this B to explore, it's in the stack, so we are going to explore. From B, where can I go? From B here, I can go to A or I can go to C. So I can go to A or I can go to C. So once in the exam, you are going to have such a question. I don't want any one of you to feel blocked. You keep the logic and you keep working. Even that, I'm sure at some point, you will be thinking that this A, I'm already exploring. Keep working. It's okay. Now for now, you keep considering that this A is unseen. There is no problem to mention it again. This is the very basic version. And next we will see how we may have a visited list and we can ignore the visited nodes. But at least having a solution, even if it's not optimal, is better than feeling blocked and it's difficult. At the time, it's very easy. Okay, so now what we have, this A, there is no problem to mention it again. And now from A and C, it's done. Now we move to the next node, which is D. So from D, where can we go? S or C or E. S, C, or E. Same here, you may see the S and you will think, as I'm already exploring, there is no problem, keep going, because the logic of this algorithm says that you keep exploring layer by layer, even if you are coming back, there is no problem at this level. So we are aware that we are not having the optimum like BFS, but at least a correct version, okay? So with this logic now, we are done with this node D, and we are going to move to the next node, which is B. So from B, I can go to A and C. Okay. From B, I can go to A and C. But as here I have this B node already exploring A and C, so you can mention it again, or you can move to the next one. And like this, you are going to come up with finding your goal, which is G1. Done. Okay. So in this case, if we want to have the solution, I was giving you the possibility to enter like a text, which is the path for submitting the assignment. So one possible path here, using this algorithm, the BFS, is to go from, we come back like this, and so to check the parent, to know which is the path that we took from S to the goal. So the final like path is to go from S to A and then to reach to the goal, which is G1. Okay, so there was no restrictions saying that you need to reach to G3, or there are 3 goals to each, like you are going to reach first, there is no restriction. So this is an acceptable solution, okay? I will give you like few seconds maybe to take this, and we will move to the other like variant of the BFS algorithm, where we are going to use data structure having the visited nodes, so that we may have a more optimal solution with less visited nodes and there is no redundancy. Okay, you can take this.
Could you possibly move next to the board again?
Okay.
The camera is on you.
Okay. Okay, for those online, you can pause and take a video because it will be recorded, so no worries. You can take a screenshot right now and it's done. Done?
Yes, thank you. That's what I
Great.
needed.
Okay. Is Zoya here? Online?
Yep, I made it in. Zoom is
Everything
fixed.
is okay? I'm just reading
Yeah.
your email.
My
Okay,
computer had an update, so
Okay. Okay. So this node B, as we are exploring, and we were mentioning that from this node B, we went to both A and C, so it's okay to mention. To visualize more how optimal the algorithm is. So if you are ready, let's move to the next one. Okay, so the concept now is saying that sometimes like I don't want to see redundancy in visiting nodes again and again, and I may keep visiting them. So the idea of BFS, to ameliorate it and make it better, is to have some data structure, which is a list, having track of all visited nodes. So I have here visited nodes, which is a list. Whenever I will be done with some element or node, I will be adding it to this list. Whenever I am coming to a new node, I keep checking if this has been already explored or not. Okay, so we go again. So our starting point or initial state is the node S. From S, where can we go? We can go whether to A, B, or D. It's the same logic. So from S to A, to B, or to D. Okay, now once I'm visiting all the child of a given node, I can mark it as done, and I add it to the visited list. Okay, so here my S is visited. If at a given moment I am having S somewhere, I will consider that as a dead node and I will not go forward. Okay, so now I have my next node with respect to the first one coming, which is A. So I will go this way. We will finish with A first, and A is having which nodes? Child B or D1. Okay, and next. So A, as soon as it's both nodes are explored, no one is making me remember to add to the visited list or explored. So we have A here, okay, and it's done. From A, I don't go like this, just I need to respect the waiting list where I have B waiting. So B is having which nodes? A and C. Okay, so when we are coming to B here, it's all done, all set. But before, did you, we finish with D first, okay? But you need to start checking. I have B. It's in the list. If at a given moment you will see B, just let me know, okay? I will not let you know, okay? So now from D we go to SC. Are we going in the right? From B we went to D. From B, there will be extra points for those who are going to be awake.
A is already visited.
A
It's already visited.
is already visited. So A here is a dead node. Okay? Even before, okay, this A is a dead node. Could we consider that B is a dead node? Let me check.
In this case, before going to C. No, so we have to respect the level.
You are right. I don't want at the time of the exam you feel like this and you say, oh, B is already there. No, B will be considered there only if I'm already checking it at this time. Is that clear, everyone? Online. Okay, so next from D, where we will go? From D, I'm following your instructions, guys. S,
C, and E.
C,
But S we already.
and
E.
E. So what we did if we are coming at the same point, please? Anyone can explain.
You can ignore S. Yeah.
Yes. This list of the visited nodes is made to stop you from visiting that node. For if you are having B already in the waiting list and you are going to explore it, there is no need to come to B here. If you are having the A already explored, okay, there is no need to check this A here. And the same with the S because it's already the initial state that has been explored. And so it's reducing these like nodes. And you can see that in this case, we have few nodes, but if we are in a bigger space, so the result could be more clear. So now from A, where we could go to the goal. And like this, we are coming to the goal state, okay? Both are giving the same like way, but one of them is giving a better solution, which may consider it like a more optimal representation, okay? Online, is that clear?
Can you go over again when B specifically will be considered a dead node?
Okay, so here we are having S, okay? I'm adding S to the list because I am exploring all the kids of, or the child of S. If a given element is the child are added now, A, B, and D. So I'm already having B in the, let me call it waiting room. And if I am coming here to visit the B, shall I go for it? No, because I am going to explore it already. It's in the queue. Is that clear?
Yeah, that makes sense.
So
Okay.
it's not under A. I can't exactly see
Yeah,
super clearly.
yeah, I will
Okay,
try
yep.
to upload a more clear like
Yep.
correction, but for now we will not consider
Gotcha.
these nodes thanks to the visited list and thanks to the information we have about the nodes that are like going to be explored, visited and going to be explored.
Cool.
So for in this case now, let's not only have the visited list, we also have the path. So the path is going to be the same from S to A, from A to G1 to the goal. Okay? S, A, then G1. Is that clear? The path is from the initial state to the goal state, which steps or states I'm going through. Okay? Next, now we have another like important information that could be added in this case, which is the path cost. How much now to go from S to A? It's the sum of, it's the cumulative sum, which is going to be from S to A, it is 5, and from A to J1, it is 9. So you have the cost is equal to the sum of 5 plus 9, which is 14. So as simple as this. Is that clear? So in this case, we suggest having a more optimal representation where there is no need to explore. Like for example here, from B we can go to A and C. If we are stopping at this level and considering it as a dead node, there is no need to visit whatever is coming next. Is that clear? Okay.
That makes
So
sense.
I will stand here for a few moments. Cheers. Okay, a screenshot is done, so I will let you guys take the correction.
Now you keep saying correction. Was our homework due today or before this class? Because online it says it's the
Jeremy,
15th.
I was mentioning that always I will give you time, okay, until 15, because sometimes it's asynchronous class. And for those online, they may say, we will be watching later. Sometimes the video taking too much time to be uploaded. So I give you more time, but I keep eyes on whoever submitting first. I keep eyes, if you are doing the little effort, you will get reward for that. So don't worry.
Gotcha.
Yeah.
Thanks.
Welcome. Are you done? When we move to the DFS, done. We move. Okay. Are you done? Okay. So if the BFS respects the FIFO Q, what does the DFS respect?
Last and first.
What?
Before last and first.
Yep. So we have here the DFS will respect the is the last in, first out. Okay. So with the same logic, we will go first time, like you need to provide some logical solution, and then you will make it more optimal. Okay. So now we have our initial state, which is S. From S, where can I go? A, B, and D. Okay. Now S is done. Yeah, I have a question.
How do we consider how to go from a level to another, from the right path or from?
I was mentioning in the slides that for now we consider always the priority is to the right, but it's random. You can have the same logic, but in a reversed way. I'll put it in the mirror and they'll see it the same way. So at the end, you will find the practice same. Yeah. So from now for S, we are exploring all like next nodes, and from A, where can we go? From A to it's you
B and G.
to B and
G1.
G1. Okay. So what logic always you keep in your brain that you need to follow? So
To go in there.
you have the Q. So always this one is the recent one, the last coming one. So it's the last treated one. These you keep them waiting. Okay? Okay?
The priority is from the right to the left.
Yeah, we are like making a deal that we will be
Okay.
working this up.
So did we flip it on the last one?
Hmm?
Priority was on the left side for BFS, and now it's on the right side for DFS.
No, it's not the logic is different.
Right.
Now we are coming, the last one is going to be the first one. Last in, first out. Before it was, like even in the presentation, I was already mentioning this. So always keep in mind, BFS has as a representation something like this, level by level, like this, and then like this. And the more levels you will have, the more you need to go through all the levels first. As per the DFS now, because this is why, because you are having the logic of, yeah, first in, first out. Otherwise, if you will keep everything same and just change the logic with the last in, first out, what representation you will have? You will have the representation of DFS, which is always going to treat the last one and its last, for example, given the given nodes from this last one. So if you are going to try to represent that, it's kind of going like in depth. This is why it's called the DFS, because it takes one node and keep going in depth. Is that clear? So this visual representation is not due to the right to the left or left to the right. It's due to the logic behind each algorithm. One is based on the first in, first out, and one is based on the last in, first out. Is that clear?
Wouldn't we start with D, if it was last in? Because priority goes A, B, D, and then D is the last one, so last in, first out, then we explore all of D.
No, now we are saying that we'll be considering it with the right side.
Oh, we swapped it for
Yeah,
this specific.
yeah, this is what I
Oh,
mentioned in
that
the
makes
slide.
sense.
This was your question? Okay.
Makes sense.
So for now, what we have to explore B, D1, B, and D. So from here, I will start this one. Suppose that's coming the last one. Okay. So from B, where can I go?
C.
Yep.
A.
To B can take me to A
A.
and
C.
C. From A, I can go to
B,
B
J,
G1.
and J1. From B, I can go to. If you will not stop me, I will never stop.
It's a visited.
Yeah. So what we have here is that we have that loop we are talking about last time. So you see it now visually. Now, if you will keep visiting like this, it will never end. So you will never come to the goal, which is just right here. Is it okay? So the problem that we are discovering here, even if you are trying to reason during the exam and you find this problem, you try to think how we solve that during the class. So I am supposed to be a little bit awake, and if I am going from S to A, from A to B, and A, I'm hearing the same letter again, I will try to consider as a dead note. Okay, so let's repeat the version of this DFS algorithm with considering this optimized light version. So we will start with S. From S, I will go to A, B, or D. So S is done. From A, I can go to B or G1. I keep going in depth, okay? And from B, I can go to A. Here I say, wake up. If you are not waking me now this time, I will be waking up. Wake up. This is a dead. I consider it as a dead end, okay? Stopping here, okay? So, okay. So if I'm coming to this dead end, now what I have in my list waiting for me? D1. So I am coming to the go.
When we add C to B as well.
What was your name? Sorry.
Dallas.
No,
C.
C,
C.
sorry. Excuse me. It's C. Okay. So that is it. It's now solved.
And then we would continue with C.
We are reaching to the goal.
Oh, fine. Yeah.
It was in the queue. Yeah.
So do we stop immediately once we hit one goal, or can there be times where we have to find all the combinations of goals?
You know, we have to continue
before,
because we have
Which one we are not visiting?
we have to visit C and
And then the rest of C
before G1.
before coming back to the
before going.
You
to
don't mind
G1.
coming?
I'm sorry?
You don't mind like
Sure. What can I do you for?
okay.
Finish the rest of
Yeah.
the path? Well, yeah, if we're going in depth, then we skip over G or and continue to B, if this one's priority. I'm not sure, because we flipped it on the first one, and I kind of got a little confused.
Yeah, you're right.
But then if we go from C, then we got G2, we got F, and then we got back to S. But S is a dead node, so
Great job.
we skip that one, and then
Okay.
F, of course, then we got G3. Sorry, I have terrible handwriting. Let's see. Yep, that's a goal. There's goal, and then S is dead.
Good job. So you have extra points for today.
Thank you. Here's the thing.
Welcome. So I will know that. So, is it clear for everyone? This is how we get extra points.
Yeah, that makes sense.
Okay. So I give you like a few moments. Otherwise, I will be also sharing like the correction in the classroom. So what is the problem with this like DFS algorithm that you can see right now? If you keep going in depth, what is the problem?
You can miss the most optimal route.
So how to solve that?
Consider the costs.
Well,
We have seen one variant.
This is an unsearched. We can do a searched algorithm. That would take in consideration the goals and go further closer to that direction. With the
This
path-
is not
with-
wrong,
With the
actually.
path cost.
This is not wrong, but I'm expecting something which is in the context of DFS. So this first execution shows that if we are visiting some nodes, we need to be careful from the loop or redundancy, okay? Next, we were solving this problem. We are discovering that if I keep going through the depth, I can at some point get stuck and maybe the just solution is right there, I'm missing, or you understand? So the solution here is that we already seen during the class one variant of the DFS, which is suggesting a solution for this.
Not talking about Dijkstra, are you?
Greedy.
Not the greedy, but
The cost,
the,
UCS.
not that one. Think of it. You have the right to go back to the slides. And you will have extra points. But I want you to do it by yourself.
Could you repeat the question?
The question is, if I consider this version of the DFS, I have this problem of that I keep going deeper and deeper. So it will be like time consuming, space consuming, and it's too much complicated. So what is the solution that proposes to use DFS in a smarter way?
Was it iterative deepening DFS?
Yes, exactly. So just before leaving, I will take the names of those. I'm getting extra points, so you're getting the extra point. So we are going to go through the iterative deepening DFS.
Can we have memorization as well?
Yes, this is why we're introducing this. So how it will be working? Okay, the DFS is there each time, but in order to control all this like length or depth, what questions we are going to keep asking? If even you can check your slide. So how it works, what is the difference between the typical DFS and this variant of DFS? The
Set
iterative.
a depth limit, right? And then you cover everything to that depth.
Yep. So each time we are going to introduce the depth limit, and each time if I am, it's kind of like mixing the advantages of this one with the disadvantage of this algorithm with the advantages of the previous one. So each time, for example, I am visiting one node, what am I going to say? I'm going to ask. So I will be initializing my depth limit D equal to, in the start, D is equal to 0. I'm still not exploring any depth, okay? And each time I am going to like run the DFS algorithm, I am going to ask myself, am I coming to the goal? Am I coming to the goal? Am I coming to the goal? If the answer is no, only then I will be like adding +1 to the value of D, means equal is going to D equal to D +1. Is that okay? Each time, until I will be going through all V visiting all the layers, okay? Means at the same time, I am going in depth, but also I am keeping my eye if there is some goal nearby, okay? So it's going to be the same almost approach. Expect that all this like depth is not going to be explored. So how to do that? I am coming. I will not write. I will keep it on this one, but I will be uploading other collection. I may use colors to make it more clear. So, okay, the red one. So each time I am going, I have my S, okay? So the first level is done. Now, I will start exploring the next level. So I am going, and I'm going to increase the value of my D, which is going to be equal to 1. So at this level, what I will do, each node visited, I will be asking the question, is this a goal node? No, then I will move in this direction, okay? Is this a goal node? No. Is this a goal node? No. Okay, so that's it. I keep going in depth. So I'm reaching to the B. Is this a goal direction? No. So before going more in depth, what shall I do? I just try to take a look first. Is this a node direction? It's a goal direction, a goal node? Yep. So this is my goal. So in this case, we don't go through all this process. Is that clear?
So now it's becoming
Makes sense.
more like.
Yes, it's inspired, but as I'm telling you, it's mixing the advantages of the BFS with the advantages of the DFS. For sure, we are always in AI searching the optimal solution. There are different logics. Each logic is having its like strong points and weakness points. So we try always to mix from here and there. And this is what actually researchers do. This is what, even while you are like, do not only learn, try to analyze if I have this plus this, if I come up with a new like algorithm or something. So this is how it works. Okay? So I give you like, I think nothing to take with this mess, but I will be uploading. Yeah.
I'm curious, so if we didn't use the what was it called, itemization, or iterative deepening?
Mhm.
If it was just standard DFS, I forgot to write the D on the F. So we would never explore the B and D up top.
Yes.
F would then continue to D, and then that would go to E and then to G3. So we would never explore those top two. Makes
Yes.
sense.
Great. Any other questions? Sure? Clear? Online?
Yeah, makes sense.
Okay. So now we are done with like this homework. What I can suggest, so you can go with the same like graph representation, try to execute different algorithms. For example, the uniform cost search of Farah. For example, if you are interested in the A star, and each time you will see that you are coming to the goal. It depends which goal. G1 is different from G3, but the cost also matters, okay? So, and try to think of for you which is the best algorithm. Otherwise, now, so I will not add this as a homework, but if you will do it, so it will be good for you.
So I want to make
So-
sure I'm understanding the homework assignment right. We're just writing down the path each algorithm would take and then how it would get to the goal, right?
Yeah.
Okay, perfect. Thanks.
So something else is that we have already seen in these are examples of an informed search. We can try to solve this with the informed search, for example. Why not? If we have some like missing information. So what could be the added like thing to solve this with the, for example, A star algorithm?
Directions.
Means
Directions.
we already have the direction. This goes from S to A and this from For example, A to S is not allowed. So the direction of the rows is already there. The cost is already there. But what makes the like
Priority.
unformed, yes, priority? Or if you go further and try to go through the A-star algorithm again, because I remember last time I was going so quick through the A-star algorithm. So we can go through that again.
This time we didn't cover A-star algorithm.
We went then very quickly through the greedy best first search, right? So it was clear, I remember, but to move to the A-star algorithm, we need to revise this first. So what do you remember from the greedy best first search?
That's someone that tries to minimize path cost, right?
Yeah. So most of the algorithms, they try to minimize the path cost. And each time we compute this cost and find different values. We can compare algorithms based on that. But the cost is always there. If this type of algorithms is informed, like what makes it informed?
They have some knowledge,
Knowledge, which is mathematically represented by,
path cost.
no,
The heuristic function.
the function, heuristic function. So here we have the main idea. I want, whenever I'm saying, for example, BFS, your brain is saying FIFO. I'm saying DFS, your brain is saying LIFO. I'm saying GBFS, greedy best first search. You will say, now I'm formed. I have some mathematical function, which is F equal to H of N, and this is my guide right now, okay? So this is the key for this algorithm. So this function, we went through this example, and we said we do not only have the different costs, because here, if you can see, while connecting in Romania, like problem, from one city to another, there is a cost, okay? In kilometer, for example, the distance, okay? And for going from Arad to this one, Bucharest, how to choose the best way? Based on this informed search, there is one additional information, which is this list. And this list is giving different numerical values. These numerical values, they represent what? You are in the exam, you are forgetting everything. Just use your brain. Close your eyes and see there is one city having 0. Always look at the extreme values. That will help you to solve, to understand at least. If this is having 0, and we are saying that this is our destination. If I am in the destination, there is a function which is 0. It means that this is my guide, this is my heuristic function, okay? And I am going to start from Arad, which is mainly the almost highest, among the highest values, which is it's very far. Still, I'm not reaching to that goal. You can see that even from the map, okay? So keep the logic. Now, how to explore this? We were saying that from Arad, where can I go? I can go here, there, or there, okay? From these 3 next cities, what can I do? I can, how to choose this one to go in this direction? I'm not going with respect to the last in, first out. I'm not going with respect to the first in, first out. I'm going somewhere in the middle, based on which logic? I am based on this heuristic function. So how did I choose to go to this one? From CBU, I have two numerical values to come. One, coming from this city, I try to find its name in the list. One coming from this city, I try to find the name, and I will compare. My main object is to maximize my heuristic function or to minimize my heuristic function.
So
Minimize.
I'm waiting for Jeremy to say minimize.
sorry, I didn't want to interrupt anybody in class, but I don't think you would pick that one based on the heuristic function.
Then
I think you would pick Fagaras.
which one?
The Fagaras, I don't know how to pronounce it right.
Yep. Because, yeah, he makes sense, because Fagerhouse is 176.
Has 176 instead of
And
193.
Has 193.
1 second.
So with the function, that one's closer to Bucharest.
Yeah. This one or this one, but so the first one, this Fagaras, it's how far?
From Bucharest?
176,
From Bucharest,
and the other one are
193.
193. So we are going for
Fagerhouse.
the, which one? The list one.
The
Okay,
middle.
are we already going, thank you, Jeremy. Are we going to go to Pitisti, the next one, or we are going to straight to Bucharest?
Straight to Bucharest.
We need to finish first all the notes, and then we are going straight to Bucharest. Is that clear? Okay, thank you very much.
Mm.
Is that clear, everyone? I
Yep.
can come back to the same, but the main idea is that I need always to respect these numerical values, and I need always to go to the minimum value, but always keep in mind, before visiting all the nodes at that level, okay? Then I go to the next level. Is that clear? And this was the remark of Jeremy. And this is what I wish that most of you can do in the exam, because we keep finding the out and we go through this same mistake, okay? Clear? Okay. Any questions online?
I don't think so.
Great. So now we went through this example. So if my goal is, I will be here this morning. So if my goal is going to be in this side and my starting point is here, so I will keep exploring. From this point, I can go here, 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 or here, okay? So which are more near to the goal? Is it the 1 and 4 this side, or the 2 and 3 this side? Which are in the side of the goal, more near? It is
2 and 3.
the 2 and 3, because it's in this region, it's more near, okay? We can see that based on distance, okay? And when I say distance, I don't want that everyone will be thinking about what type of distance.
Minimum.
What?
Manhattan.
Yeah, in this case, it's the Manhattan distance. But when we say distance, it's usually the Euclidean distance, which, for example, if I want to go to Farah, I will go straight. It's the Euclidean distance. It's just the shortest path towards the goal. If I will be respecting the Manhattan distance, it means that I will not go straight. There is some, like here, there are like walls or something. For example, I want to reach Farah, but I need to go through some like of the students. So I may choose to go here, not straight, you see? Then I go to the next one, and the next one is going to take me to Farah. Is that clear?
Yeah.
So this is the difference, and we are going to explore in the AI class many types of distances, but now keep us with the Manhattan distance, which means these numbers now down, they mention this type of distance. 1, and here we find 7, which means that this point is 7 steps away from the goal. Means, for example, I will say 1, 2, 3, 4, 5, 6, 7. Okay, I won't consider the walls for now, to make it simple. Okay, because if my algorithm is having like knowledge about how far we are and the way to take, why don't we go straight? Okay, it makes sense. So from 3 here to the goal, I need to take 1, 2, 3, 4, 5 steps, and this is why I find 5. So now we are understanding those more near to the goal are having like less like distance, they are more near, and those which are in the other side, they are more far. This is why they are having a bigger values of the Manhattan distance. Okay? So what we did now, we will keep like choosing. If I want to choose between these two or these two, I may go for 2 or 3. Which one is coming first is the one I'm going to visit. The 2 is first, so it will take me to 5 or 6. Then I will keep respecting the distance and moving until I will be reaching to my goal. Is that clear? So Here we are using only the information about the distance, and we are introducing the Manhattan distance, okay? In the different other algorithm, which is the A star one, besides the like heuristic function, we need also to have an idea about the cost, the current cost from one node to the other. So here, our evaluation function is going to take f of n, which is the sum of g of n and h of n, which g of n is the cost so far to reach n, and f of n is the estimated total cost of the path through n to goal added to the estimated cost to the goal from n. Is that clear? We will understand more with the example. So we are not only going to focus on this list of heuristics we have, okay? We will also consider the numerical values on the arrows because it makes sense. So if I want to choose between moving from arad to, for sure in the start I will explore all the nodes and you need to keep that in mind. And if not, for sure Jeremy will let us know. And so we will have from this point arad to the next city, the cost, I will have an evaluation function, which is not going only to be that heuristic over there. It's going to be the sum of the numerical values from H plus the actual cost to reach from this city to the other one. So the actual cost is 118, and I am going to add to that 329, which I am bringing from the list, which is here, okay? And I keep doing that. So I need to have track of each time the final value of this, my heuristic function, okay? So from here to here, I have 447. From here to here, the sum will give me 393. From here to here, the sum is 449. And which one I'm going to choose is the least, because I always want to minimize my heuristic function. So this is why I will keep following this path. Again, now from 447, 413, 393, and 449, which one I'm going to opt for? Which one?
The 393.
Exactly. And so on. So here I need to evaluate first, and then I compare with whatever I have there. If it's mean, I go for it. If it's not the mean, I go for the mean. Is that okay? Clear for everyone?
Yep.
Online? Great. Okay. So here we have 600 is too high. So we keep following the less cost until we reach to our destination with 450 cost this time. Okay? So now we are done with the A star algorithm. So this one is, no, so this is the way. And so this algorithm, we can go for it like here. Each time, besides the function, I will add the distance, which is 1 plus 7. In the start, I'm only one step away from the initial state. Then I will be two steps away from the initial state. I add that, how much far from initial state plus how much is left for me to reach to the goal state, which is going the sum of Manhattan distance to the goal state plus Manhattan's distance from the initial state. And like this, I keep minimizing the my heuristic function until I will find the path towards the goal. Is that clear? Last time?
You kind of sped through it right there, but I thought the 1 plus 5 on your 3 spot would be explored before the 1 plus 7 on the left. So
One.
right.
Excuse me. Okay, we come back to this step.
Okay.
Let's do it again together. So here we are clear. I'm respecting the order. The first one is 1, 2, 3, 4. Okay, and then we have the cost. The cost is here. This side is 6. This side it's 8. So it's clear that we will go from the 6 side. So the 6, there is the 2 and the 3. So which is coming first? It's the 2. So this is why we're exploring its neighbors first. From here, we took 2 steps from the goal, which is 0, 1, 2, plus I have 1, 2, 3, 4 steps to reach to my goal. So I have here 6 and my function it's 4 plus 2, 6. And here I have my function is having 6 plus 2 is 8. So, and don't forget that somewhere you have 6, somewhere you have 8. So here, the less, so we are supposed to go to this one because it is 6 already. No, this one is first. So 3 is coming first. So we are going to follow this one. Is that
Okay.
clear?
Yeah, that's where I made a
So-
mistake because that's where I expected it to be, but I thought it was somewhere else. But that makes sense. Thank you.
Yeah, welcome. So if you want, we can keep it going. So from now 7, I have 6 plus 2, which is equal to, you will help me, 8. And in the list here somewhere, I have 4, which is coming first, with same priority, with same value, numerical value, which is also 8. Is there, for this 5, I have how much? If less, I will go for it, okay? I have 8, also it's the same. So how to move? I am going to respect the first one. 4 is coming before 5 and before 7. So first you compare based on the numerical value of the heuristic function, and then you see if it's coming first or not. So the priority are for those who are first, okay?
I thought a search doesn't do any FIFO or LIFO. It's strictly just priority queue.
The advantage is coming after the other algorithms. So whoever created the A star is having the logic of other algorithms.
Previous.
So he is having that logic
Yeah.
first, for example.
A itself doesn't.
Yeah. So maybe if right now we can Google it and we write A star based on LIFO stack, we may find someone coming with this idea and bringing up to the table the advantages of this idea. And it's like this that we invent new algorithms. But for now, it's like respecting the order. So it's not it's like the FIFO for now. Or just to make it simple and to understand it. Is that clear? Am I answering your question?
Can you use A independently without using any other algorithms? Just do a strict A algorithm search?
You mean about the A star?
Yes, yes.
A star is the optimum solution of the AI.
So I think he's asking like when they match, when there's a 6 plus 2 on 5 and a 1 plus 7 on 1, and they match, are we going to the lowest number first? And is there
Yes,
any?
sure. Always our main object is to minimize the heuristic function. This is our deal to start.
I meant the lowest number between 1 and 5 if they both have a value of 8. When they match our heuristic function, we can't pick the lowest number because they match.
Right.
So which of those two are we selecting and why?
We select based on the priority,
Right.
like the example of the first in, first out. It's just like we are like confirming that we will follow this step, but this is how we are learning if the A star is coming. But I'm saying maybe if it's not existing, we can work for it and invent another variant of this algorithm. Why it's like this? In order to, we need to say, okay, now we are going to execute the A star, and if the priority are same, we are going to consider the first one coming to the list, which makes sense. So it's like this, the A star works like this. If you think that there is another way to make modification, means it's your own modified or variant of the A star algorithm. It's not the A star algorithm. Am I answering your question?
Yep.
The very simple answer, if heuristic function is same, I need to respect which is coming first to serve first. If until here the answer is done. If you are that much like curious about what if I start with the other one, I explore another way and all, you can do that. It's not the A star algorithm, but we can come up with a different algorithm, okay? But the A star, if I am having the same value, so I will be serving the one coming first. Okay. So it's done with the A star algorithm. So the difference now, if you can try to visualize, if you are using like having this problem representation with contours, okay? And you're having your starting point here and your goal here. The way that uninformed, like, because explore the space, it explores it this way. So we visit this like volume. And if you see how it's working and how we are visiting the space, like the maze before, with respect to the A star, so it does not take you to the ways that are far from the goal test. It takes you from paths that are more near. It always guides you thanks to the heuristic function. Is that clear? Okay. Yes, any questions? Okay. No. Now, okay, here just the difference between the Euclidean distance. Sometimes we cannot access to the Euclidean distance as I was like explaining. So we go through the Manhattan distance, means through the CKs. I cannot go straight to the point. The Manhattan distance here, for example, to reach from this point to that point, just an example here to explain the Manhattan distance. But I think it's clear for everyone. If someone is not understanding the Manhattan distance, please let me know. It's exactly like if you are having, so you have your X and Y plane here, it's 2D plane, and you want to move from point A to point B. How you consider the Manhattan distance here? It's the difference between the X coordinates of B minus those of A and the Y coordinates of B minus those of A. Is that clear? Which is a different distance from the Euclidean one, which is the square. Okay, so I wish that everything is okay. Otherwise, never hesitate to send me emails. Okay, so applications of A star are, there are multiple applications like video games, like pathing, like resource planning problems, robots, and language analysis, and so on. It means it's a very useful algorithm because if you have an algorithm that is really reducing the search space from all this space useless like memory, storage, time consumption, and all towards a more like limited space, it proves only the power of this algorithm. So now we are done with the A star algorithm. We are done with our homeworks. We are done with the search algorithms. We are going to move to a new topic, which is the adversarial search or gaming strategies. So previously what we did, there is a problem, AI problem. There is an agent, which is one. Like, for example, there is a problem, there is a goal, and I want to reach someone to give this pen, for example. It's only me, the agent. So there is only one agent. When we are in the context of gaming, we consider more agents. It depends on the complexity of the space, but at least we can study the case where we have two agents. So if I have two agents, I will be having the same problem that I want to solve. But if, for example, you are trying to maximize, I want to succeed, for example. For sure, there is someone who wants me to fail. If, for example, you want to win, I don't want you to win. Okay? So it's like this. It's struggle between me to win and you are trying to not let me win. Okay? So here's the idea. And here we are like dealing with some conflicting objectives, which are one wants to maximize his like winning value, let's say, score, and one wants to minimize that. So here we have a different approach for still solving this kind of problems, which having different names, which are the adversarial search. One of the examples is the tic-tac-toe. It's just a pencil and paper, sorry, game. I think if you have fun now, we can play it. But I really had fun, by the way, playing it online. I'm keeping the, you can right now try to access via your computer or phone. Let me, if you will win first time, then we will stop it here. Because I have been trying first one and the second one also. The Gomuku also, it's really interesting game. So try to explore it with the computer, because it's not the same if you are playing against the computer or against the human. So take some time to play with the computer. So once you will have the logic, we will be able to understand things. And there is a difference between having the logics of this game when it's like going to be played with a human and when you are having it with a machine. Anyone winning here? Are you serious? Are you
I
serious?
just won one.
So the winners, your call, you can come and show us your strategy.
Okay, thumbs up. You know,
Because if I'm going to show, it will not
it's
work.
really interesting. Tic-tac-toe, you can always win or always tie.
Yeah.
True. Yeah. You can master it. And you can never lose if you play it right.
Okay. So what was your strategy?
I don't know, man.
I don't know. So-
There's certain moves you take. I used to play softball.
So I think you are having a strategy now. So I will call you to explain your strategy.
Sure, let's see what well, it's based on whatever the other player
Yeah.
does, and then I make my move from there. So if he's taking the center, then I take the corner.
So you have the O already there. You are going to have the X
Then I
and
take the corner, then he does that. So it's gonna be a tie game. I know this already. So the game is washed. Yeah, basically. So we can go anywhere, just don't let him win.
yeah.
So it's a tie game. We'll do another one.
So you are not winning at the end. No one is winning, right?
Nope, you can always tie or
This
win.
is one of the approaches. So it's not always that if you are having the strategies, you are going to win. So he's having the strategy, and his strategy was taking him where? To make the computer, which is the advisor, what is it? Adversary, sorry. So he's letting the adversary fail. So he's not winning, but in his mind that he's winning because the adversary is failing. So this is what
I
you're
one that mostly works most of the time.
yeah.
You just take
Okay.
the corners on the opposite side of wherever he goes.
Yes, but if I may ask you, which is better, you lose or no one is winning, you say no one will win. But if I will say you must win, then here you need to really find a strategy that you will win. You will maximize your chances to win. Okay? So, and this is what the computer is doing as well. Okay? So, for example, here we are going to go quickly through the introduction because you guys are already familiar with the concept, with the game, and now we are having conflicting like objectives. If we are having our environment here, which is the tic-tac-toe board, we are having the agent A and B. A, for example, is the computer, B is one of you playing. So each time there will be an action or a move from the adversary, we are going to consider that, analyze that, and react based on that, okay? So this is the approach. And how to win, for example, is the main question that we are going to ask here. If we are going, so I'm asking you as a human how to win, but what if I ask you, how can you make or program that machine which is also doing its best to win? This is the question. So this is thanks to the algorithm. And in this case, we need to first think if we have a problem. The problem is coming from the real life. This problem is coming from a pen and paper. So we are having it already here. So the main, I don't know, it's like this. How to represent this to the machine is a very important first step. So from X and O, does your machine understand X and O? It doesn't. So what does the machine understand?
Numbers.
Numbers, numerical values. So how are we going to let's say, translate or represent this problem with numerical values, not only numerical values, also a clear representation. So this representation could be search tree. We were already dealing with the search tree in the start. This is before, but could it really be a search tree in this case? No. So the search tree is having the nodes here. We can consider them the gain states. Means the state, for example, this is a state. So you can consider this as a node. If I am going to add the same state, I am going to add another element, the green one, for example. This is another node, which is another state. So before, the node would only contain some letters, some alphabet, some numbers. Now, if we are in a different context, what will stop you from considering that your node contains this information? Nothing will stop you, okay? So, and the edges, because if we are having our graph, we have nodes connected thanks to that edge. So the edges are going to be the moves, the steps. For example, if you are going to insert an X or it's going to insert an O, for example. So we could like model the same problem with the same approach with nodes and edges, okay? So, yes?
How can we have the same tree if we have two agents?
It's not the same tree. Okay, this is an excellent question. So if you are, for example, one of us is going to be the computer. You are the computer, I am the human, for example. So you are going to play and it's your turn. So from here, from this node, you are going next to move to the other next level, which is going to give me hands to play, okay? So for me, I cannot only have this solution. This is one possible node I can take me, but I can take different actions. So you will be having, this is the computer. Once it's giving me like hand to play, I can go whether to this node, to this node, to this node. But all this level is representing me.
So my move will be the parent to the moves of my adversary.
It will be like, one time you are playing, one time the computer is playing. So one time the computer is playing, so then it's giving you hand. So after that, you are playing. It's how many like possible ways here, representations. So it's 9. 3 by 3. There are 9 possibilities here. So from these possibilities, you cannot go at the same time in the 9 possibilities, otherwise game over. So you will only choose one. So based on your choice, the computer is going to react, okay? So if you are going to choose this one, the direction is going to be different, like different decisions, different results and outcomes. So this is why the search space now is the same idea that we are having. This is called transition model if we are going to respect the terminology of first time. So this transition model is going to have the all different or possible nodes that I come in thanks to a given transition. These nodes are represented by the states, and this is the state space. Okay. So it's not this. It's 9 factorial. So I cannot even think of it. So from all these possibilities, we need to have some strategy so that we reach to the optimum. Okay. Or what is the optimum now? 1. Or the strategy to win? We are already discussing this. So we are going to work with some algorithms. If we are already having some background knowledge in AI now, we are not going to use that because why it's not valid? I can ask such questions in the exam, by the way, just try to understand my thinking. So why I cannot use the search problems in this case? Why I don't use DFS, BFS?
DFS doesn't have a goal.
I have a goal.
Well, it doesn't take it into its search. It's uninfluenced, right?
No, I have a goal. I
We
have
have
different
the goal-
states.
the goal
I have
is-
the same representation. I have transitions. I have goal. I have. So what is the difference? Why I
But they
can?
have two agents.
Yes.
Oh,
See?
because it's not a single goal that you're going for, it's two people fighting each other.
Exactly, because we have two agents. Great job.
Huh.
Okay, so as we're having two agents, we are introducing new algorithms for this such of problems. So one agent want to maximize his own like score. At the same time, he want to minimize the score of the adversary. Okay, so this is the min max algorithm, which is one of the effective ways. Let's say in the start effective. So we explore it deeply, and then we'll discover if it is or not. So it is one way to solve this tic-tac-toe problem or search problems. So the problem with this, because the space is huge, it's only because if I am taking one step or I am coming into one state, I'm not sure that the adversary, what he's going to do. It's not always that he's going towards the goal. Sometimes, I don't know why, we call it, if we are playing to the, oh, stupid, why are you doing this? Or so it can happen that he's choosing a different way. Maybe he don't see the results now, but maybe in the future, it depends, okay? Because the state space is huge, you cannot explain it, and this is why we are talking about uncertainty. Okay, so we don't know which future moves that are going to be taken by the opponent. And the optimal strategy now is that we need to consider the worst case scenario. Worst case scenario means that our opponents is not like going to have any problems, always going to be like doing it the best way and always choosing the best move, okay? So if we consider that, we will not lose, okay? So we have this strategy. So the min max here for each move, we are working on minimizing the maximum gain among all our opponents' potential moves. Okay, so how now to define the gain value for two sides? And how to obtain gain values from our non-terminal nodes? How can I take I'm not winning. I'm how to reach to that step that will take me to my goal. And how is going to be defined this gain goal? How am I going to evaluate? It's like this, and I'm going to show to a human or a machine. I don't understand anything. So we need to maybe quantify things. We need to have some numerical values, some representation, and so on. So this is what we are going to do. We are going to define gain as utilities from the perspective of one side, from perspectives of X, for example, and also from the perspectives of the other side. We are going to affect like numerical values like 1 or -1 or even a 0. In that case, no one is winning, for example. And like this, for example, if we have in this like setting, the O is winning, means the X player is losing. If it's a loss, we can say it's a -1. So here, if no one is winning, so it's a 0. And if the X is coming to its main objective and it's winning, so it could be represented by a 1. Okay, so these states are -1, 0, and 1. And each time the player is going to maximize or minimize the score. So here, if we're considering the winner is X, means the player is the X player, okay? So this player is having function max of X aims to maximize the score. Maximize the score means 1, so he's winning. Or between -1 and 0, what would it be the max? 0. 0 means no one win, it's better than he loses. Okay, and the min of O, the O player, he wants to minimize the score, which means that aims to minimize, in this case, means what? For him, minimize, the minimum value is -1. So in this case, he's winning, okay? Otherwise, if he is between 0 or 1, which value is going to be chosen?
0.
0 because he minimized so that the opponent do not win. Is that clear? So I think that the representation now is becoming more like mathematical and clear. So we may have to represent each like element with a numerical value. Then now to answer the question now, how to obtain gain value for non-terminal nodes? Here we perform the recursion. I don't know if you are familiar with this, but it's like the loop. You are going to do the same treatment again and again and again and again and again. Loop. Okay, so you are going to perform recursion up in the gain tree until the terminal node. So we call the gain value at each node as the max mean value. Okay, at each time we are going to evaluate this value, max mean, and we will see. Now, let's go further and have some notation. So let S of 0 become the initial state, like always, S initial state. We have a function, player of S. This function is going to have S, which is the state, and we are going to, it's going to return its whether the X or O turn to play, whose turn to play, is going to decide about the player, okay? And the actions, which has the arrows before, so which way am I choosing? Or it's going to return the moves in state S, the possible directions that I can take, and result of S and A, which is a function, taking a state and an action, it's going to return what will happen to this state after taking this action, okay? So we will go with, we have some examples for this, but before that, how to know if we are like winning or losing is thanks to the function terminal of S that checks if S is terminal state or not, which is going to return Boolean number or true or false. For example, yes or no, or 0 or 1, okay? Is that clear, everyone, please?
Yep.
Great. Okay. The utility is the final numerical value for terminal state, and it's based on this utility we are going to evaluate who is winning, like 1 or for X is winning, 0, no one is winning, or -1, it's the O winning. Okay, so like this, for example, we have this empty like board. So it is representing the initial state, no one is taking his turn. Then we need to decide who is going to start playing thanks to the function player of S. So this function is going to return who, for example, let's start with the X player, for example. So if the X player is playing now, player of S, in this case, what is going to return? Oh, because we know that it's one time for the X, one time for the O, and so on. Is that clear? Okay. So we have another function X, action of S, sorry. The action of S here is going to take S, which is a state, and if I will take an action up in this, like, take what can that be? If I will insert some O, for example, where can I like add? I can add it here, for example, or here. Is that clear? Possible like results of the action of S. And then the result, which is going to take state and action. So let's consider this is the state, and the action is to add an O there exactly. I'm specifying the location of that O where I'm going to add. So the result is going to be the representation of the board, combining that both action on that, taking that state. Okay? Please, clear?
Yes.
Okay.
Yep.
Great. So the terminal now, we need to evaluate, is this a final state or is it like, it's similar to the goal before when we had the tree, it's similar to the goal state. So is this a terminal state or not?
No.
So it's false, it's returning a Boolean. And then this one, yep, so it's true. Okay, so utility now is going to have that numerical values that's going to evaluate if it's winning, losing, or no one is winning. So in this case, what we have? 1. The x is winning. In this case, we have
Minus one.
-1 because the O is winning. If no one is winning, it will be 0. Okay. So let's explore now together the tic-tac-toe game. And if you will focus with the slides, each time I mention, for example, the right child is added to frontier first, just to make a deal together that this way what we are going to respect, okay? So left child returns values and or is expanded first. So we are going to start with the right child. So from this state, where can I put my x if I am the the x player? There, or in the other empty space, or in the other one. These are my only 3 possibilities. If now I will give turn to O to play, and it's going to go from this state. So where O could put his mark, it's whether here or here, okay? So like this, we create the tree that explores all the different possibilities. Now coming up to the last one, where there is no empty space, no one is there to play, we need to evaluate. Here, for example, we have 3 x's in the middle, if you can see. So it is the x1 winning, means numerical value, utility equal to 1. Otherwise, here, okay, it will take you to the utilities equal to 1. If you will go in this way, if you will go in the opposite way, you will not win. So it will take you to -1. And so on. So we keep exploring our tree like that. The O players mentioned whether you put it the O here or here. If I'm going to follow this one, the O is winning means -1 because the O is winning. Otherwise, if I have still options here, no one is winning and I am having 0. So here the max is maximizing his chances at the same time minimizing the chances of the mean and vice versa. Okay, so here this path will not take me to win, this one will take me to win. And when I say take me, it means the player at this level, okay? Is that clear? Okay, so now we are having this representation and we know which path will take me to winning or losing. So I can choose. So whatever for example, if I am a computer and I have all this algorithm to execute, whatever my opponent is going to take as action, I already have the plan to minimize his chances to win. Is that clear? Okay. Now we have a different type of games, which is a more abstract representation of this same tic-tac-toe game. But in this one, what we have aroused. Once going to the up, it means I want to maximize my value. If the direction is going down, it means that I want to minimize. And it illustrates really well the idea of min-max. So the first level here, you see max, it wants to maximize. The next level you want mean, it means it wants to minimize. And so on. So here it's going to maximize and here it's going to minimize. So let's see this example. If I have this, I want to maximize this value, first one 3, 12, and -8. So which one to choose at this level of the mean?
3.
The minimum value is yes, -8. The negative value cannot compare positive ones. Okay, so here we will have the -8. Then, if for example I will be choosing from this, which is the -4. Yep. So the -4 is gone. It's done. Now from these, what I will be selecting? 2. So when I will be moving to the next level, I will be having opposite thinking. So I want to maximize, and the maximum is the positive number, which is 2. Okay. So like this, we are able to find a way to represent this problems and solve them probably. Okay, solving them by search algorithm, which is the min-max. So let's have this quiz quickly. Again, -9, -7, 2.
-9.
-9.
-8.
-8. 4.
4.
and 4. Okay, great job. So now again, we will come back to the tic-tac-toe game. And if here I want the same logic, we went through this slide, I believe. Yeah, so with the same logic, sometimes I want to maximize, sometimes I want to minimize, and I will have this representation of the space. Just a quiz, but we were already going through this one. Okay, in this case, what we were using, we have only like one objective, one value that we are working on maximizing or minimizing. Okay, but now if we have more than 2 players, 3, 4, 5, you can have even up to 10 players or whatever. So you cannot use this logic, but you will use what is called utility vector. So there is a difference between comparing here numerical values. If you have 1 player, so you compare only the utility value for each one. Kind of evaluation cost or something like this. It's similar to the cost that we had before. So now what you will have is a different representation. Let's suppose, for example, you have, instead of 1 player, you have 2 players. And then you will be having utility vector having the utility values of each of them. Like this utility vector AB, you will be having for A and for B the values. So let's see. Here, -9 will be for whom?
Probably B, like the minimum.
So see, in math, if I am saying the function is called
A.
utility vector, let's consider this is the name of the function. It takes 2 parameters. The first one is A, the second one is B. So you need to respect that order. Always the first one is going for A, the second one is going for B. I can in the exam call it utility function BA, then you need to do the opposite work. Okay. So here we have -9, 9, -7, 7, 2, -2. So what B is going to choose in this case? So here we have the max. Now we need to minimize. Keep in mind the direction of these arrows. Yeah. So the mean here is
Two minus 2.
They're all the same.
We need to minimize B.
mean. Yeah.
So minus 2. Yeah. What?
I think it's maximizing B in this case.
A. Yeah. Minimizing A, maximizing B.
Yeah.
Because it's always this one is here, this one is here.
Yeah. So maximize.
You be careful about this. Like, is that clear, Cole?
I think so.
So at this level, it's whose turn to play?
B to maximize.
Yeah. Okay. Okay, let's do it again. Now, in this case, what we will do? Think of it.
B to maximize.
-8.
Minus 8.
Which is going to be?
Minus 8.
Yep. Again.
7 minus 7.
Uh,
4.
4 minus 4.
Yep, this one's the force.
Yeah.
Yeah, Farah, you need to be careful. So, and here, we need to do the opposite. So we're going to stick the 4 minus 4. Okay? Because it maximizes. So here's the min max values representation here for a given node n. If the n is terminal node, so this will take the utility of n result. If n is max node, the max value of n is the max of n successors values. And if n is a mean, it's the opposite. Okay? Next, now what we will see, we are going to, given a state S, max is going to pick the action of S that produces what? Its name is max. So it's going to maximize. So it's going to choose the highest value of mean value result of S. This is a function, and we will be working how to write this function, how to reason in order to find this function. And opposite for the mean, it's going to be the opposite. So the mean is going to pick the action N that is going to produce the smallest value. One wants to go up, wants to go down, okay? For the max value of result of S and A. So now we need to define these functions. Yes?
We're at time.
Okay. Thank you for letting me know. Okay, so we'll see this next time. So we are stopping in the functions. So it's almost done. So we are done. Next time, there will be no homework in this case. So you did well. Okay, any questions online?
It was
Okay.
actually really good information. Cleared up a lot of stuff. Thanks.
Okay, so.
Thank you.
Welcome. Oh, your names. I need to have it. Just you can write. So get an extra font. It's you, Farah, Jeremy, and yeah. Oh, thank you. Okay. So next time you must have extra points. Jeremy, I'm writing your name.
Okay. You're still recording, by the way.
Okay, I'm just saving that I'm writing your name. You will have extra points.
Yeah.
It's recorded now, done.
Yep.
I cannot come back.
Yep.
Okay. See you.
Bye.
Bye-bye.